Good morning, everyone. I am Rohit, and along with my teammate Mugil Vanan, we are proud to present our final project, WipeShift, formerly known as AGIS, the Agentic Evolving Guard Intelligence System. Under the guidance of Ms. R. Gayatri, our focus is bringing autonomous machine speed defense to enterprise wireless networks. We initiated this project to solve the critical asymmetry in modern cybersecurity. Today's network infrastructures are incredibly complex, and human defenders simply cannot react fast enough to automated machine speed attacks. Furthermore, while AI is being used in security, it's mostly passive, just generating alerts. We lack AI that can autonomously fight back in real time. Finally, relying on cloud based AI raises serious data privacy concerns for sensitive enterprise networks. To solve this, we built an end-to-end autonomous cyber operation system inside the Cyber Cluster simulator. We created a competitive zero-sum environment where two fully localized LLMs battle each other. The defending Blue Agent is powered by Microsoft Pi 3.5 and attacking Red Agent is powered by Qwen 2.5. Using action masking, TraumaDB episodic memory, and distributed LoRa fine-tuning, these agents continuously learn and adapt without human intervention. Our work is broken down into three core pillars. First, the Aegis framework, which integrates GenAI into multi-agent RL pipeline. Second, our learning methodology, which isolates these agents so they learn independently using memory and replay buffers. And finally, validation, where we test if these simulated training policies can actually hold up against real world security tools. To ground our research, we conducted an extensive review of recent 2025 and 2026 literature. I will now briefly highlight the key takeaways from these papers, specifically focusing on how frameworks like Hackfire and React approach agentic AI, and then this brings directly to our comparative analysis, which maps at SSCAP. As you can see, standard RL relies on single-step reactions. Recent LLMs frameworks like Hackfire or React improve upon this, but they still rely on cloud APIs, centralized nodes, or scripted non-adaptive attackers. Our project Aegis completely shifts this paradigm. They pit two local LLMs against each other in a competitive zero-sum environment. We replace standard replay buffers with ChromaDB statistical pattern extraction, and we execute everything over a hardware isolated distributed network, solving the exact limitation left by these previous ones. As we saw in the comparison, existing systems still face major hurdles. There is a massive skill deficit where human analysts are too slow, and a scale bottleneck. Associate teams can monitor everything at once. Traditional IDS firewalls fail because their rigid rules can't catch zero-day exploits. Ultimately, the biggest hurdle for autonomous AI is bridging the sim-to-real gap, training agents that can actually understand complex, dynamic networks rather than just reacting to static scripts. Novelty. Our project introduces four key novelties to overcome these challenges. First, this is the first integration of active, localized LLMs into a competitive RL loop. Second, we developed a dual layer masking protocol that completely eliminates LLM hallucination. Third, we use ChromaDB for semantic memory to prevent the AI from forgetting its strategy. And fourth, we democratized the hardware by running distributed LoRa fine tuning strictly within consumer grade DRAM limits. Looking at our proposed framework, we enforced a decentralized training and execution topology. This means the agents are physically separated. They cannot see by looking at each other's memory. They fight over a 13 host enterprise network, navigating a strict zero sum game using a 52 dimensional observation space. To make the AI intelligent, we use an adaptive curriculum that slowly scales the difficulty from basic reconnaissance to full-scale exploitation. Our validity filters guarantee the AI only makes legal moves, and through episodic memory, the system retrieves past successful strategies and injects them directly into the LLM prompts as a hint for its next move. Training these models continuously is a very hardware intensive. We optimize this using 4-bit quantization and LoRa fine-tuning by carefully managing our VRAM and programmatically offloading models from memory to prevent OIM crashes. The agent communicates them rapidly over a direct Ethernet TCP socket, maintaining complete isolation. This architecture diagram illustrates the flow. On the left, PC1 hosts the Cyber simulated engine and the Blue Defender. On the right, PC2 hosts the Red Attack. As you can see in the handshake diagram, they communicate in a strict two-phase step block flow. PC1 sends the network, halts its simulation, and waits. EC2 runs its inference, sends the attack action back, and only then does the environment advance to the next system requirements and tools. We achieve this using two physical Ubuntu machines equipped with NVIDIA RTX 4000 GPUs. Despite having 8 GB of VRAM available, our system is optimized to run efficiently underneath that ceiling using Python, PyTorch, or Llama, and Unsplunk modules on this business. We orchestrated this through four core software modules. First is the environment and training infrastructure. This interface directly simulated to firmly cap the load action spaces. It features a strategic course that injects instant micro bonuses to reinforce good decisions and an autonomous safety regulator that monitors training health and passes fine tuning if loss thresholds are exceeded. Second, agent subsystem. It completely decouples the GenAI from RLO. It built a hybrid action selector that automatically boosts critical defensive actions like server restorations and uses a decay algorithm to slowly forget its early failures. Third, for memory and pattern extraction pipeline. We utilize a vectorized database to filter out poor experiences based on strict reward thresholds. At the end of every episode, it mines the raw logs to extract successful patterns, injecting highly actionable, summarized details directly into the AI's next prompt. Finally, our distributed communication model. To maintain speed and zero leakage, we replace heavy HTTP APIs with raw low latency TCP sockets by using synchronous step blocking and strict message farming framing. We guarantee that the simulation has exactly been needed, preventing any network packet fragmentation, keeping both physical machines perfectly synchronized. Empirical results. We evaluated the system over 1,000 episode run. This took about 40 hours. The results were highly successful. Both agents achieved over 84% valid autonomy. We also proved our hardware optimization with VRAM taking a peak at around 4.4 GB. Most importantly, we observed a massive behavioral shift. The blue agent autonomously learned the network priorities. It stopped wasting time on low-value external nodes and focused entirely on defending the critical OP service zero, executing proactive protective actions were nearly 10,000 times. Here in the implementation screenshot, you can see our reward time. Yellow bars indicate the difference. Post bonuses kicking in. This proves that even when the red attacker successfully breaches a subnet, our system still mathematically rewards the blue. To show you exactly how this looks in practice, we'll now run our live split screen demonstration. Let's dive right into the execution. If you direct your attention to the right side on the screen, you are looking at the backend terminal of PC2, the red agent's isolated machine. You can see the initial TCP socket handshake completing perfectly. PC1 and PC2 are now synchronized and episode 1 officially begins. Now look at the SOC dashboard on the left. In the top right corner of the dashboard, you will notice the kill chain indicator currently reads Recon. If the, in these early steps, the red agent is quietly executing network discovery actions. Just below that, at the network topology map, all 13 hosts across the user enterprise and operational subnet are solid green. The network is completely secure and the blue agent is actively executing monitor and threat hunt actions to search for anomalies. As we cross step 10, the environment dynamic changes entirely. On the dashboard, the kill chain phaser escalates to expert and then escalate. Watch the network topology map closely. You can see the user subnet host flipping from green to yellow, meaning they are compromised, and then to a dark red, meaning the attacker has gained privileged access. Notice the terminal on the right. The red LLM is rapidly firing exploit remote service and privileges commands, but the blue agent is fighting that immediately. Look at the reward timeline graph in the center of the dashboard. See those spikes in the bonus points at the bottom. That is our autonomous blue was injecting these micro bonuses. Every time the blue LLM correctly issues a remove malware or restore command on a compromised host, the system instantly reinforces that behavior, keeping the AI's learning rate stable. We are now in the mid to late stages of the episode, and the tension peaks as it becomes more laterally to the enterprise subnet. Look at the action distribution pie chart on the left side of the dashboard. Notice how the blue agent's behavior shifts. It stops wasting its compute cycles monitoring the completely compromised external user nodes. Instead, strategy becomes proactive. The LLMs relies on its PromoDB pattern extraction and realizes the threat is moving deeper. It begins deploying decoys and aggressively isolating the enterprise subnet to break the attacker's pivot chain. As we approach the final steps, the kill chain phases its impact. The red agent is making a direct run for the crown jewel OP server 0. If you look at the blue action field, you will see it repeatedly executing restart, restore OP0. This is the strategic emergence we discussed earlier. Blue generative model has autonomously deduced that defending this specific operational server neutralizes the attacker's highest reward potential. On the cumulative reward chart, you can clearly see the blue line stabilizing, proving it effectively holding the network score against an active machine speed assault. Finally, we hit our step 100 and the episode concludes. The dashboard updates with the final artifacts declaring the episode verdict. But the autonomous loop doesn't stop. Watch the terminal on the right very closely. The episode ends and the raw fine tuning cycle instantly triggers. You can see the unslog framework loading the model weights and running backpropagation based on the experiences the red agent just stored in the vector DB. The models are updated, memory is cleared, the TCP handshake re-establishes, and the next episode begins automatically. This is continuous, self-sustaining. This brings us to the end of the presentation. We successfully built a localized hallucination-free MARL pipeline that trains generative AI to defend networks autonomously. Thank you.